Carnegie Mellon University's Advanced Database Systems course is filmed in front of a live studio audience.
Guys, like I said, I can't be there for the first week of classes. I'm out here in California because somebody needed my help and had to come and ask me to do something weird out here, and so that's why I'm not in Pittsburgh the first week. Right? It's always something. Oh, like, Andy knows how to deal with the. Go have him help us out, or like Andy knows something about databases. We go have him help us. But it is what it is. So right now I'm out here in a parking lot with like a bunch of drifters and hanging out. But I figured now's the time to go through the class. Let's plow through this. So this lecture is not really going to be about the course material. It's really about what the course was going to be about, and then the logistics of like how the project's going to work out, because that's going to be a big component about 15-721 this semester. I want to spend time talking about that. So it's going to be different than everything, the previous incarnations of the course. So I say it's always every semester. Why should you take this course? And the straight answer is basically that databases are still in demand. They're super complicated to build, super complicated to maintain and optimize. And there's a lot of really interesting unsolved problems in data processing and running queries and analytics. So this course is going to prepare you for either career or research into database management systems. And the great thing about it is, like, even if you don't want to go down that path of like doing database systems work, the things you're going to learn about in this semester are going to be valuable throughout the rest of your life. So if you can write a code in a database management system, you can write code in pretty much anything else. Like anything else that's going to care about performance, it really needs to understand what data is, what the workload is, and how to take full advantage of hardware. And the great thing about it is also too is like people pay you a lot of money for it. It's part of the reason why I'm out here in California to deal with all that mess. And if you don't believe me, here's a quick overview of some of the students have taken 721 for the last 6 years or so. And these are just the ones I can quickly remember off the top of my head. And they all end up at awesome places getting paid a lot of money to work on database systems. So hopefully, if you come along with this semester, we'll put your photo up next year. So, and Databricks has surprisingly hired a lot of the best students more recently. But everyone goes everywhere, which is always good. All right, so this course is really about the understanding and learning about the modern practices of how people build a database management system, and the techniques and the methods we're going to use to do systems programming to develop out those ideas. And this semester we're specifically going to talk about analytical workloads. So we're not going to really talk about transactions or doing write-heavy workloads. It's really about how do I have large data sets and run queries on them quickly to extract new information and new knowledge from the databases, or from that data. And so the goal is, in addition to understanding all the methods and techniques of how people build a modern analytical database system, you'll learn how to write good code that's high performance and correct, how to write documentation and testing plans for that code, because it's not enough just write, hey, here's our project, we're done. We want to have full-fledged testing methods and ways to ensure that things are operating correctly or things are producing the correct results. There'll be a little bit of code reviews during the semester, and then obviously working on a large code base. Maybe not entirely true for at least the projects in the beginning, but since we're doing semester-long project this year, your code base is going to get quite large by the end. So we're really focusing here on state-of-the-art topics. We're not going to be sort of rehashing stuff that we covered in the intro class or going through the textbook, right? It's really about looking at the latest research paper and the latest literature on building a modern system, and then seeing how we can apply that to our own. So at its core, the overarching model of the database system we'll be trying to build or develop will, at a high level, look a lot like the stuff we covered in intro class, like a classic database system. But it's really about how do we then infuse these ideas and these methods that have been developed the last 10 years or so to accelerate query execution. So on that topic, these are the topics, or these are the main ideas or sections we're going to cover throughout the semester. So first, we're going to talk about what the data actually should look like. So the data formats, how we're going to do encoding and compression in such a way that that will speed up data access, but also reduce the footprint of our databases. We'll start talking about different methods to accelerate query processing. So doing vectorized query execution or code generation or query compilation, like how to take a query plan, physical query plan, and execute it the most efficiently on the data. Then we'll sort of look at a larger view of the system. How do we handle scheduling within a single query itself and across the entire workload? How do we do how to run join diagrams efficiently? How do we handle network protocols, but between the nodes and between the nodes and the client? We're going to spend a lot of time talking about query optimization because, again, it doesn't matter how fast we build our database system. If our query plan is suboptimal or just garbage, then all the stuff we're going to do before then doesn't actually matter. It's a waste of time. And then we're going to spend a significant third of the lecture, a quarter of the lecture or semester, talking about or looking at real implementations of database systems. And this by reading the papers from the major players in industry and startups and sort of seeing how we can then apply or how they're applying all the techniques that we've been discussing in their particular systems. And we'll essentially form a taxonomy where it'll say, okay, a system can do X, Y, Z, and we would then see how like Snowflake does things or Yellowbrick does things. And so we'll cover that throughout the entire semester. So for this course, I'm assuming you already taken the intro course at CMU, 15445, 645, or something equivalent in your own undergraduate background. Right? This is a graduate level course on modern database systems. We'll talk about the classic algorithms, like how to do a hash join, but we'll talk about how to do it in a modern setting on today's hardware. So there's a bunch of things I'm not going to go over as background, like relational algebra, storage models, basic memory management buffer pools, and so forth. Like all of those things we're going to discuss. I'm going to assume you already know them, and it's really about, okay, how do you do a high performance modern parallel hash join, right? That's cache conscious or so forth, right? So that's really the flavor for the discussion throughout the semester. For the course policies and schedule, please always refer to the course webpage. I've posted that this week. It needs to be updated a little bit with some of the readings later in the semester will get changed up a little bit. But for at least the first couple weeks, the schedule is pretty set. And then we'll talk about what's required for you or deliverables throughout the semester. But again, I'll just say as we go along, obviously don't plagiarize, don't try to steal things, don't cheat. And if you're not sure, please come talk to me. If we do catch you cheating in some kind of way, which again, for a graduate level course, this should not be an issue, then we'll have to refer you to Warner Hall. And that's not good for anybody. All right, I'm going to have my office hours twice a week, immediately after class, 3:30 or 4:30, in my office on the 9th floor in Gates. If this time is not convenient for you, send me an email and then we can try to figure out something else. So, I'll say this every semester. What can we talk about when you come to office hours with me? Well, we talk about, your status on the project, how that's going. If you have questions about the papers or want to know more about the particular topic that go beyond the things we discuss in class, happy to talk about those things. A lot of you are going to want to get database jobs at the end of the semester, so we're going to talk about how we can facilitate that. And like I said, I know how to handle the police up to a certain extent. Obviously, if you try to run from that, I can't help with that. But whatever. Again, if you're getting involved in databases, you're going to be ending up in a parking lot, teaching classes at some point or doing something shooty. So by all means, talk to me before we have problems later on. We have one teaching assistant this semester. That's my number one PhD student, William Zhang. So he's actually CMU undergrad. I think he graduated at 4.0. He actually took this class when he was a sophomore and crushed it in a way that's suspiciously good for a sophomore. But he's legit. So we asked him to stick around, and he's continued with his PhD after spending a little time at Single Store, which is a database company. And, he's working with us now, and he's fantastic. So he's the TA for, as we get further along in the projects, he and myself will be the combination to us. Will be helping each group with their implementations. He's Canadian. it's fine. I mean, he's been good to us, so there should be no issues with that for anybody in the course. And if you have a problem with this, let me know. All right, all the discussion for the day-to-day operations of the course, and just as we go along in the projects, we want to do the Piazza. If you have a technical question about the projects or anything, again, post everything on Piazza, so we can all contribute as a class. If any personal questions or anything that's not related to the project, any logistical things, just send those emails directly to me. All right, so here's the breakdown for the grade of the semester. So there's going to be 4 parts, and as you can see at the bottom, the semester-long project, that's obviously the bulk of the grade. And so if you're a PhD student, this course counts for, I think, the software systems elective. And this is the reason why is because we're heavily focused on the projects. So I'll go through each of these one by one, but I'll spend most of my time at the end talking about the semester-long project. So for every class, except when the groups are presenting their project updates and so forth, there'll be a assigned reading. So if you look on the schedule, there'll be 1 paper per class that has this crown next to it, the icon to indicate that it's the primary reading. So this is the one that you're responsible for. If you want to go beyond the topics in the course, like if it's related to your project or you're just curious, the other readings are considered optional. And some of them I'll cover in the lecture, but like the assigned reading is the main one that's sort of like the canonical, provides like sort of canonical description of the technique we're trying to cover, or like the most important version of the technique we're trying to cover. So for all these primary readings before class, you have to submit a synopsis through a Google form at the URL there. And the idea is here, you'd read the paper and then summarize what the paper is actually trying to tell us about, or what method is it trying to show us. And by writing it down, it forces you to really think about, okay, do I really understand what the paper is trying to say? So the synopsis is not meant to be like a really long book report. It's really just be like a quick summary of what the key parts of the paper is. So you have the first part is like 3 sentences about what's the main idea, like what context are they trying to describe this particular method, and what are the key findings or takeaways from the paper. And then like a 1-sentence description of like what system they're going to use in their evaluation. In some cases, it's obvious because it's like, oh, the paper's from Snowflake, so they're talking about everything in the context of Snowflake. Or it might be like they hacked up Postgres or DuckDB and put it in that. So like just understanding what was being modified, what's being evaluated, that would be super useful. And then the last one is describing what workloads or benchmarks they're using in their evaluation to test their particular ideas or method. And the reason why this last one is important because when it comes time to start testing and evaluating your projects, I don't want you to come and be like, hey, what workload should I use? You should know because you're going to see a bunch of these things over and over again throughout the entire semester in these papers. So again, they have to be submitted before the class starts, and everyone is granted allotted 3 skip workloads during the entire semester. Okay. So again, the whole point is for you to learn learn something from the papers. So it doesn't help you if you just go take the paper and dump it into ChatGPT and answer the synopsis, right? You don't get anything out of it. So please don't do that. If there's summaries of these papers that you find on the internet, just don't copy them in. Don't copy from your fellow classmates. Again, we will have to go turn everybody into Warner Hall if you get caught doing this. So don't be stupid. All right. In addition to the synopsis for every class, there's also going to be each student's going to be required to write lecture notes. Think of this as like a longer version of the synopsis, but also covering all the ideas and other papers we're discussing in the class, which may not have been included in the single paper assignment. Right. So the idea is like you watch the lecture and summarize the slides and the key things that we're talking about into notes, and I'll have examples what these look like. We'll put everything on GitHub. We'll put everything on the course website. We'll make these available to both the current students in the class because it'll help on the final exam, but also in future years and people outside of CMU. So again, these notes should just be sort of limited to the things that we discuss in the slides. oftentimes students will ask questions and I'll start saying crazy stuff. That does not be included. Like anything about the slides is sort of the key thing there. So every student is going to be assigned to do this once per lecture. Problem is that we have more students than lecturers, so I got to figure out how to handle that. So right now there's an administration spreadsheet. There's an assigned lecture date with everybody's Andrew ID. That one we got to figure out how to load balance that accordingly. I don't care who does what. So if there's a topic you really want to cover and you want to swap somebody else, by all means do that. You don't need to ask me for permission to do that. Just go ahead and do it. And for this one, you're allowed to use ChatGPT or whatever you want, right? Because we don't care, because it's really about like you're using it as an assistive technology to help you flesh out the core ideas or things you want to capture in writing. So by all means, like if you want to take the transcripts from the videos and put that into ChatGPT and let it summarize it for you, but then use it as the starting point to then flesh it out further, go ahead and do it. But in the end, you as the student are ultimately responsible for what the lecture notes are going to say. So ChatGPT starts going off the chain and starts saying things like, actually, one year I said I embedded like column store stuff, which is not true. So if ChatGPT starts saying BS and you put that in there and turn it as lecture notes, well, no, you didn't vet that, and you'll be docked for it, right? So obviously, again, be smart using modern technology. All right, there'll be a final exam. That'll be take home, long form. I'll give out the questions at the last day of the class. And then you'll turn it in whenever we have the final exam, final presentations during finals week. And again, this is not meant to be, it's not going to say, the questions aren't going to be like, okay, what does this paper say about this particular thing? The idea is to see whether you can synthesize a bunch of different ideas from the various materials you talk about throughout the semester, and then put them in a new context, like a new theoretical system or something like that. Just to see, again, you understand not just how individual ideas work, but how they all sort of fit together into a larger system, which is sort of the key thing that we want to focus on here. All right, so the big part of the semester is going to be the semester-long project. And the idea, the high-level idea, what we want to do is we basically want to start building a new database management system here at Carnegie Mellon, both myself and the other professor, Jignesh Patel. And so the course is going to basically be the sort of starting point for fleshing out some of these components we would need in this larger system. And so one of the overarching themes we're going to have for how we design things going forward is this adaptivity. So not just the idea is like, can the system automatically adjust a query while it's running, or adjust itself while it's running based on the data that it sees or different characteristics of the hardware? And can we do that incrementally over time? And again, I'll explain what that is as we go farther along, but that's the overarching theme is sort of in that direction. We decided to do everything in Rust this semester. Like I said, I did not know Rust before this semester, and as I send the email to you guys, I know a lot of you don't as well. So we're not going to teach you Rust. We'll just sort of pick it up as we go along. We don't know what name we have a name for this system yet, but which is always one of the hardest things to do in computer science. But the idea is that we could take all these components of the different projects, put them together, and make a full-fledged system. Maybe next semester in the fall or the summer. So I have a way to kind of name systems, but right now it's names to be determined. So the way we're going to do this is that every group every student is going to be assigned to a group, and we have groups of 3. And then there'll be 5 topics or components of this larger system we're going to end up building. And the idea is that we have roughly 30 students. We would do 10 groups of 3, and we would have 2 groups assigned to build the same component. And so they'll have to collaborate a little bit, make sure that they figure out what the specification of that component is, but then they're also going to compete with them and try to build a faster or better implementation than that particular component. And at the end, we'll have a vote to decide who gets, which component of the two, of the same topic is, which implementation of the same component and the same topic is the winner. And we'll use that going forward in future research and future projects. So everything I said here is true except for the optimizer group, and I'll explain why that's different. But the basic idea is because the query optimization is so hard, and we only have a semester, it's unlikely anybody's going to build a query optimizer in a single semester. So whereas the other components, we could build a working prototype fairly quickly in a small group. So the idea is that we will, for the optimizer team, they'll have to collaborate together more so than the others. All right, so there's 5, as I said, there's 5 project areas, or project topics. The first 4 here are the ones where, again, they will have 2 groups and trying to implement the same thing and compete against each other. So the first is going to be a scheduler. This is the part of the system that figures out, here's the queries I need to run, how do I break them up and send them to different nodes? And then as the queries are running, how do I keep feeding, or sorry, as the queries are running, how do I keep feeding tasks to the nodes that keep them saturated and always busy? The execution engine are the parts of the system that's going to take those tasks for the query plans and actually start executing and processing data. To simplify things, we're going to assume that the execution engine will be a single node. The next component is the catalog service, and this is going to be the internal database files and keep track of the database files and the schema. And this will then be fed into the query optimizer and the scheduler to figure out, okay, here's the data I have, here's the tables I have, and how to generate the physical plans for those. And the last one here will be the I/O service, the thing that's actually responsible for going out to disk or an object store, retrieving the blocks of data that are needed by the system, and then distributing them to the various nodes as needed. Then also can maintain its own local ephemeral cache so that we don't have to do expensive calls to the object store. You can just read and write things from local disk. Then it says the query optimizer for that piece, the idea is that SQL query shows up, and then we want to use a combination of role-based optimizations or heuristics and a cost-based search to determine the best physical plan for that query. We do have an existing prototype now that a student worked on last semester called OpD. It's a fork of Data Fusion, which we'll explain what that is as we go along through the semester. So it follows the Data Fusion's internal format for query plans, but it doesn't rely on Data Fusion to do join ordering and other things. So again, building query optimizer is super, super hard. We're not going to get we're not going to get too far in a single semester. And so the idea is, like, instead of having 2 groups, build redundant things for this part here, it makes sense for them to work collaboratively, different parts of the system, different parts of the optimizer, but working on potentially a single code base. So for all the other projects, we want to implement this from scratch. We're okay with you taking heavy inspiration from open source things like Data Fusion. That's one thing we're looking at in particular. There's another one, Velox, from Facebook or Meta, for their execution engine, but that's in C++. So we're okay with you, everyone just looking at these things and discussing them if it's open source, and if we figure out how to borrow these ideas and put it into our own system. So throughout the semester, there'll be 4 projects, 4 milestones. So the first one coming up, January 31st, will be the project proposal. I'll explain this in a second. Then there'll be 2 status updates once a month, and then at the end of the semester, whenever we're assigned our final date in May, then we'll have the final presentation, and then everyone will be required to do the code drop on GitHub to turn in their systems. But again, the idea here is that by having these incremental updates, and even in some classes at the end we have extra time, we can just sort of discuss how everyone's, the progress everyone's doing on their projects and anything that is coming up, any problems and issues amongst everyone. And that way, like, it's not like everyone disappears without any feedback and then they show up at the end of May and be like, hey, here's my project. How did I do? Like, everyone's going to know how everyone else is doing, and we sort of see how all these things sort of fit together. So, all right, so the first thing coming up on the 31st is in 2 weeks, will be the project proposal. And this will have 3 parts. It'll have a plan, like 1 or 2 pages of a markdown file describing how you're going to actually implement the thing, the part of the system you're going to be working on. And then you give a 5-minute presentation to the class and say, here's the high-level ideas of what we're trying to do. And a key thing which you want to describe is also not only how you're going to build your thing and what ideas or what libraries and so forth that you're going to take advantage of, but actually how you're going to test your implementation to see that it's actually correct, and make sure there's no errors and problems as you go along. In addition to the project proposal itself, you also have to turn in a specification proposal for what the API of your component is going to be. So you can sort of think of these 5 projects as all sort of microservices, and there'll be an internal API that's going to allow one project team to call your service to get whatever it needs. So like if the execution engine team, they obviously need a physical plan. So the query optimization team or the scheduler team is going to have to give query plans in a format that the execution engine team can actually use. So we want to be up front and figure out what this API is ahead of time, so that everyone knows how to talk to the other parts of the system. So the API should cover like what are the commands or operations you're going to expose, what are the input and output encodings going to be. So for example, I said query plans, or like if it's the I/O service, what are the data blocks actually going to look like? Is it going to be Parquet format or something else, right? And then how we're going to handle status codes and error handling for these. I'm not going to care about authentication or any security stuff. Again, this is just a prototype for us. So all those things we don't have to worry about. And so now what's going to happen also too with this API specification is that the 2 groups that are building the same component have to implement the same API. So the way this is going to work is each group's going to have to designate one person as a liaison that's going to talk to the other group, and they have to get together to decide, okay, here's what the API needs to be, and so that way if we decide to choose one project versus another at the end of the semester, they'll implement the same API and everything will still work. And then the liaisons will maybe talk to liaisons at other groups and make sure that they understand what what is expected of the data or the outputs that they're generating. And so for the APIs, rather than write everything from scratch, because certainly 2 weeks is not enough to figure all this out, especially for some of you that are like coming at this from first time thinking about these things, we want to reuse as much existing APIs as possible. So an example would be the catalog service should just reuse the Apache Iceberg API, and just expose that same interface, and that'll save a bunch of trouble. So for the query optimizer team, CalSite would be another choice of an API we could choose. For execution engine, we could follow Velox or Data Fusion, right? So by all means, reach out to we'll discuss this in class, reach out to the TAs and instructors, and we'll figure out, okay, here's the API you should be trying to follow. These guide you towards something to look at. The other cool thing actually too, if the 2 project teams also implement the same API, then you could do end-to-end high-level testing and use the same infrastructure. So for example, like if the API is the same, then like the catalog service, you could have like, get me this table metadata. Like you could have testing code that could be reused for both those teams as long as they implement the same API. All right, so then throughout the later in the semester, we'll have 2 status updates, and this is just a 5-minute presentation in class to everyone to say, here's the status of the project, like here's how far we've made it, here's what's changed in our plan since the last time we presented, what are some of the surprises you've encountered of either how hard or how easy some certain things going to be. We'll talk more about this as we go along, but we'll enable like testing coverage checks and make sure like your tests are actually you're writing code that's actually being verified and checked in through tests. So we want to know what your coverage number is, and then if people have demos, that's always super exciting to share those as well. And then as part of this, you just keep updating your design document to say how things are evolving over time. So you'll want to basically this is what you have to turn in the end of the semester. So you just keep maintaining this document as you go along, so that it's not like you have to go write it from scratch when it comes time for finals week. And again, the liaisons are going to want to talk to each other and say here's how we're going to implement. Here's how we're going to implement certain benchmarks and tests, because at the end of the semester we want to actually do comparisons in some way, either for correctness or for API coverage or performance of these different parts. So how are you actually going to compare these guys? And then during the finals week, we'll have a final presentation, and talk about here's what you implemented, here's what you accomplished, and then how to measure the performance differences between the 2 different implementations. And so for the final benchmarks that compare your implementation against the other groups, we have nice dedicated machines here at CMU that you want to use for these evaluation. So we'll coordinate this later, but the liaisons will be responsible for actually scheduling the time and running those benchmarks. So we have a true apples-to-apples comparison between the different groups. And then lastly is that we're not going to say any project is completed until we get a final code drop, and that means all the comments and other code reviews issues on GitHub have all been addressed. We have all proper test cases. We make sure everything's sort of working, and we have nice documentation and comments in the source code. So you can essentially hand it over to the next class and let them pick up where you left off. Or in some cases, some of your students are doing master's theses or capstone projects. When you come back in the spring semester, or sorry, the fall semester, you would have something to pick up on and know how to keep continuing things. All right, so this one, again, goes without saying. You don't want to plagiarize. Don't copy code that's not yours without getting permission from instructors. Again, for some things like parts of an execution engine, you can go look at data fusion to see how they do certain things. I'm not saying they do everything correctly or the best way, but if you want to sort of take high-level ideas of how they set up the code, that's okay. But obviously, just don't wholesale copy things and try to pass it off as your own. We make sure that we know that the lineage of any source code that we're adding to this project, where it came from, and make sure that it's under the right circumstances. All right, so that's it for now. The sun's coming out. I gotta get going. So for next class, we'll have the first lecture on the first paper on sort of modern analytical systems. So this will be, I think, from the Databricks guys describing what they do. You'll want to submit the first reading review for this again before class starts, and then use that link there, and that'll take you to the Google form to fill it out. And I'll also talk a little bit more about project logistics. I'll post on Piazza, again, if you're not in a group, how to find a group and start beginning the process of writing your project proposal. Let's do it on the 31st. And then for the lecture notes, again, go check to see what your assigned notes date is. And for the ones that are where we have more students and lectures, again, we'll figure out some alternative or something else to do to spread the workload out evenly. Okay? All right, guys. With that, see you in class on Monday next week.